Hello, and welcome to the second part of this quad tree in SIG implementation video. So yeah, since last time I've been looking up a bit on how quad tree algorithms could be implemented, and yeah, I actually went ahead and tried an implementation that seemed to work fine, and I'm gonna do some small adjustments to the idea that I had about doing this. I'm just gonna do the quad tree and not have like a sweeping face for now. We can maybe add that later, but for now I'll just delete this and we will just do there's actually two different ways I want to test to do this. So the first is just to go through each body, call intersect on quad tree. So what that will do is you will call for each body. So one body gets passed into this function intersect or intersecting, whatever it's going to be called, and that will match all the bodies that intersects with this body with the bounding bounding box, and it will return all the intersections that matched this body. So that's one way of doing it, going through all of the bodies and doing that. And then another way I thought was doing it, because what I'm gonna do is on each frame I'm gonna build up the entire quad tree from scratch, and I'm gonna have it rebuilt on each frame. And it shouldn't cost that much, although it might be cost some with the number of bodies that's gonna be in the quad tree. When that goes up, then the cost is gonna go up as well. So I think in the future I might look into having a dynamic quad tree, but for now it's just gonna be a so-called static quad tree, which is built up from scratch each frame. You just shove all bodies in there at the same time, and it will build up the quad tree, and then you can do queries on it. And what I was thinking is that each frame we actually do, we want to put all bodies in the quad tree, and then we want to call intersect on each of them. However, we could call intersect after we've inserted each body, so we don't have to check. As much. So yeah, I'll show you later what I mean, but it's basically when populating the quad tree, also check for intersections for each insert. So that way it might be a little bit faster checking for intersections, having a static quad tree like that. Right, so, well, last time I built up this initial little skeleton here, but I actually want to do some changes here as well, since a quad tree is basically, it has this root node, or it's actually a page, as I call it here. A page is something that has the children, and this is actually, well, children could either be, in this case, when we have a list of nodes, it could either be the entries or the page, the sub pages. But since we always know, this is kind of coming from the R tree, like this setup that I did here is kind of coming from the R tree that I had. But in a quad tree, you always know that you always have the 4 subdivision or the 4 pages that's going to be the result of a subdivision in a page. So if I just show here, you would have something like quadrants. Let me just bring up my notes here so I can do this properly. So a page will have quadrants, and I'm just gonna define it like this because, yeah, we have a nullable of subdivision. I'm gonna explain it. So we have a nullable of subdivision. Subdivision is a type that I'm gonna define soon, but it's basically gonna have the top left, top right, bottom left, bottom right, each corner of the, or each quadrant basically of the whole boundary of this page. So that's going to be the subdivision. I also have this generic type parameter here, which basically you can just use subdivision. You can use, I'm going to use it later to show why I'm having different types of the corners. But for now, I'm just going to define this subdivision here. And it's going to be sometime t. I have to actually call it subdivision type because it's a name collision. And then it's going to return a type. And I'm going to return a struct, which is going to be top left. And I'm just going to define it as undefined by default. And we can populate it later when we're using it. So yeah, now we have this structure, which can be used to store pages. It can also be used to store the boundary boxes, what I'm gonna do later. And yeah, we're also gonna remove this children here, and we're gonna put in entries. And this is also something that doesn't exist yet, but I'm gonna define a new type called a slice array list, which is basically just an array list, but it operates within a known or owned slice that we have from outside, basically from the tree. So the tree is going to have a bunch of entries in an array list, and then this slice array list is going to look into one of the slices basically in the array list, and I'm gonna show you how I did that. It might not be like the best implementation, but yeah, this is how I did it anyway. So let's see. Yeah, so we've got the boundary box, we've got the entries, which is basically the children of the page where the entries live, so the bodies basically. And then you have the quadrants, and it's possible to have both entries and quadrants in a page. If you have entries that perhaps that are either too few to be split into subdivisions, or if you have already quadrants but you insert a body that's too large to be contained within one of the bodies or one of the quadrants, I mean, then it would have to be put into the page. But we'll go through that as well. I'm just going to define a function called can accommodate here as well. So what this will do is it will tell the caller that, yeah, we can put more bodies in here. And this is basically all it is. It's just checking, do we have enough space in entries to accommodate for one entry. So we're just checking if the length of the entries list is going to be less than the max entries in the page, in a page, which is 10 right now. So if it's less than 10, then we can put another body in there. And we're also going to define subdivisions. This is a function that when called will return a list of, or subdivisions with boundary boxes. And yeah, it's just gonna from this boundary box that's that the page is contained in, we're gonna divide it into the 4 quadrants: the top left, top right, bottom left, bottom right. And so we are going to return a subdivision, a BV, and then we're gonna say top left is going to be, so AABBs are actually a rectangle, and it consists of a top left point and a bottom right point. So the top left point of the top left quadrant will just be the top, it will be the same point. So if you do this, then it will copy over the top left point to the new structure here. And the bottom right in the original boundary box for the page is going to be all the way to the bottom right, but we actually want the bottom right of the top left quadrant to be in the middle, so that it's basically half the size. So what we do is we subtract with a vector which is half the size. We need to define that as well. And then I just put is minimal false here because, well, is minimal doesn't really matter in this case, since yeah, I just have to put it here since I'm initializing a BB, and it has that in the structure. So I'm gonna define the half size, and it's gonna be the size of my boundary box, and we're just gonna scale it by half, like this. So that's the half size. So now we have our top left quadrant. Now we need the top right, and this is gonna be top left is so this is the top left of the top right quadrant is gonna move halfway in the x-axis. So we're gonna add half x, and I'm gonna define that point later. So it's gonna move halfway across in the x-axis, and it's not gonna move anything in the y-axis. And then we have the bottom right, which is gonna be moved upwards half y. So this is gonna have to be subtracted by half y. Now let's, and also we need is minimal. And let's define half x. So this is gonna be, I have to import this ZLM library, which is basically a math library with vectors, and which I'm using. So this one is basically just, yeah, we can use half size like this. So we got half x, and then we do the same for y, except this is half size y, like that. Yeah, so now we got the top left quadrant and the top right quadrant. So the top right quadrant, the top left point of the top left, the top left point of the top right quadrant is going to be halfway across, like in the middle. It's going to be exactly in the middle of the parent boundary, at the top middle. And then the bottom right is just going to be, it's going to be moved from the bottom right of the parent halfway up across the parent. So yeah, now we got the quadrant of the top right, and we can just copy that to say bottom left. So bottom left, the top left point is going to be moved down half y. So we're going to add half y to top left. Now bottom right is going to be moved to the left. So we're going to subtract half y, or half x, sorry. So it's going to be moved to the left half x. And that's our bottom left quadrant. And then we have our bottom right quadrant, which is going to be top left is actually going to move to the middle now. So we actually add half size. It moves both in x and y direction, half of the parent boundary. And then we have the bottom right, which is actually not going to change at all. is going to be the same point. So we got our 4 quadrants, which fills up the space of the parent boundary. And yeah, that's our subdivision. So now we can use this later to calculate our quadrants sizes. Well, not only the sizes, but also the positions. So yeah, let's do the slice array list later. I'm just going to go through this basic structure here also. So we actually don't need the concept of node here anymore, because we only have pages and entries, and we know that each page only consists of its quadrants. So we're going to keep that in a separate list. And then we have the entries as a list from 0 to 10 right now. So what we do need to change here, however, is we need to make entry an AABB, or we need to add AABB to an entry. So now we got the bounding box of the entry as well. So now we also need to add a list of pages here. So we're gonna have an array list of pages, and I'm gonna store them like this. And we change this to entries, and this is just gonna be entry as well, like that. And I usually also define these things below all the custom types or the subtypes that we have, page and subdivision and everything. And I also move the initializing function down here as well. So we've got all the custom types up here. This is just how I organize it. And then we have the fields here and the initialize function here. Now we got pages and entries, so we also need to change here. Pages is going to be page, and also we actually need an allocator. So we're going to get an allocator like this, and we need to pass it in here. Forgot to do that last time. So that's our pages, and then also entries. Yeah, entry. And now for the capacity here, we actually want 2 different capacities, initial capacities. We want one for, it's not that important actually, but I'm just doing it to avoid a whole bunch of relocations and stuff. So we're just gonna have pages capacity and entries capacity, and we're gonna have initial entries capacity is 1000, and then initial pages capacity is gonna be initial entries capacity divided by the max entries in the page. You can also define it the other way around if you want to have more, if you want initial pages to actually be a nice number, I guess. I guess that's more yeah, it's probably better to just do this instead. So this is times initial page, so that we don't get some weird floating point numbers. So yeah, we have max entries as pages 10. This can be fine-tuned for performance later, depending on use case and stuff. And we also have the initial pages capacity, which is 100, and the initial entries capacity, which is entries in page times the initial pages capacity. So this is going to be 1000. And so down here, this is going to be initialized to that. All right. So in order for us to be able to access these entries, yeah, I'm probably gonna need to explain here also a little bit. So how this is stored. So yeah, I'm basically storing all pages that exist in the quadry in this one page list. And these pages then have all the pages basically have this pointer into the entries list. So each one will have their own pointer into this entries list. And this entries list is going to be all the entries. And in the end, these entries will also have the boundary boxes. Yeah, they have boundary boxes, and then they're gonna have this value as well. So the way we get this entries for each page is gonna be with the use of this slice array. And I'm thinking if I want to implement this now or if I want to just wait a little bit until we have more stuff in place. I'm just going to wait a little bit on that and show more on how the implementation works here. So what we need for the quad tree, let's go ahead and just define this the initialize function as well. So this is going to be qt here. This is just just the initializing these array lists like this. And what I also want to have is a reset function. Sorry. I want to have a reset function because I need to reuse, my thought is to be able to reuse the quad tree without having to like reinitialize all the array lists and everything. So I'm just gonna create a reset function here, which will just resize this lists back to 0. And what that does is it's gonna basically just set the length to 0. It's not really gonna do anything else. And you can even check the source code on what it does by going into here with LSP. And you can just see that, yeah, it's ensuring total capacity, which is basically going to return since the length is 0 that we're sending in here. So the capacity is more than 0, then it returns. It's going to be always going to be more than 0. And then it just sets the length. So it doesn't really do anything. It's just returning and setting a variable. So it's basically a really fast operation here. Right, so what we need for this quad tree to work is we need to be able to populate, and that will create all the quadrants, will create all the entries and stuff. So let's define this populate function. So we're taking in our quad tree. We have a boundary, which is the root boundary, which is gonna be the responsibility of the caller to make sure that the root boundary is gonna be able to contain all of the bodies. So we're sending in a root boundary, and this is basically what I was talking about last video, is like a bounded or an unbounded quad tree. So this is a bounded quad tree, which means it has a static size, and you will have to define the size at first, but you can just pass in a sufficiently large boundaries and it will work. And then we also want to send in the entries, so that we're gonna populate the quad tree with. First thing I want to do is just reset this quad tree so that it's back to 0 with everything. And then I want to calculate how many pages do I need. So, okay, what I've really done here is I've actually gone ahead and optimized this a little bit, but I'm just gonna implement this naively at first here. So what I'm gonna do is I'm just gonna say for each entry like this, we are going to insert this entry. And I'm using a pointer here because we get a list of entries like this, and it's way easier to store the pointer to the entry so we don't have to copy around these boundary boxes and everything. I'm not sure what the best way to do this is, but I've actually opted to use in my implementation, use a pointer here instead of using the copy here. So I'm just gonna change that to be a pointer, and we're gonna insert all the entries like this. And now we need to define this insert function, and we get an entry which is a pointer, and we actually I actually made it so that it returns, but let's just not do that for now. All right, so we got insert, and we're gonna then, oh yeah, because it returned a bool. But let's just worry about that for now. I don't think we need that at the top level. So we need to, so in case of grabbing the boundary box for the entry is going to be too costly, I'm just going to store it in like this. Hang on. Let me just go through this more like this. So how I did this was I actually need to start somewhere. So we need to start at the root, right? So what I did was I made another function called insert into page, and this is going to get the root, which we're going to define later, so get root. And then we're also going to have the entry, and I'm going to pass in the entry AABB, and this is where I need the AABB as well. So I'm gonna define this like this: get entry AABB of the entry, and we don't have this function, but the entry get entry AAB can actually be passed in as a comp time variable here. So we can say get entry AABB, which the type of this is a function which takes a pointer to the entry or the value. Yeah, well, the entry type here, the entry dot value type, and then it returns an AABB. So the user of this quad tree is able to pass in the type of the thing, which is usually going to be like the body, and then a function that takes a body or pointer to a body and returns an AABB. So that way we don't have to know how this is retrieved. We just say that, okay, we want to basically cache it here. So we get the boundary box and then we pass it along to this inner function as well here. So we need to define this insert into page, and we're gonna do, yeah, let's see. So we're gonna get the entry, which is pointer to a type, and we need the entry AABB, which is an AABB. And this function, just bringing up my notes here, is going to be, well, so when inserting into a page, the algorithm works like this. So first you check whether or not or my algorithm works like this. First, we check whether or not the quad tree page that you're in, which contains a boundary box, you check if the page can contain the entry's boundary box. And if it can, then we go ahead and do stuff. If it can't contain it, then we just return out of there. We abort because we can't contain it, so we can't do anything. So we're gonna check if and I have a function called contains here on the AABB structure. And if you can't contain it, then we have to return. And also, I'm going to return a bool, so I'm going to return false whenever we cannot basically have accommodate for this, or not accommodate, but we cannot contain this thing, then we return false, which means that we need to have this thing here to avoid the error. Let's see. So, oh yeah, we also need the page here. So page, let's do a pointer like that. Right. So, okay, so if we don't contain it, we're going to return false. If we can contain it, then we actually want to check, do we have any quadrants? If we do have quadrants, then we're going to do some stuff. We'll get to that later. But otherwise, if we don't have quadrants, we're first going to check if we can accommodate. So can accommodate, and this is can accommodate, as we defined earlier, is just going to check, do we have room in our entries list? And if we have room in our entries list, then we can just insert the entry into the page, and we're basically done. So we're just going to say page.entries.append, which we haven't defined this yet, but we're going to. Probably a good, let's see, so we need the entry. So we're basically creating an entry here with value is going to be, entry. And the boundary box is going to be get entry AABB. Wait, no, we already have the AABB here. So like this, yeah. And yeah, that's basically it for the can accommodate branch. And then we return true because we have consumed the entry basically. And then if we cannot, we'll define the slice array list in a second here. But if we cannot accommodate and we don't have quadrants, then that means we have to split. So we have more than 10 entries now in our, or we have 10 entries already, and we try to insert another one, which fits into our quadrant or our page. So we have to make quadrants now. So what we do then is we say we want to subdivide. We haven't defined this yet, but we actually just do this. And this guarantees that at the end of this function, we actually have our quadrants populated now. So yeah, I'm going to define another function, which is called insert to child. Maybe this is better if it is named insert into quadrant. Or something like that, because it's gonna need a special, basically what we're doing is we are trying each quadrant. Can I fit this entry in here? Can I fit this entry in here? And so on until we succeed, or don't succeed and it returns false. But we will probably succeed because we are containing the, actually, I just thought of something. This could make it so that we end up with an orphaned entry right here. Yeah, that's gonna be. So if none of the quadrants can contain the entry, then yeah, that's interesting. So then we just return false and we don't actually accommodate, even though we have split the page and we want to put also, I think I forgot something. I I haven't divided the entries into the quadrants either, which we probably want to do. But anyway, let's leave that for later. This is maybe a bug here. I mean, it's only a bug if the body is large enough to not fit into one of the quadrants, but it fits in the parent. So then it will be orphaned, basically, because we're just returning here. We're not doing anything with the entry after that. Okay, anyway, I'm just gonna put a to-do here to remember that. If none of the quadrants can contain the entry is orphaned. Okay. So, and also here, I'm gonna say, should we divide the entries, the existing entries, into the newly created quadrants? Not sure about that. But okay. We should probably like reevaluate their, like where they should be and stuff when you split. Let's see. So yeah, this function is probably the busiest, like with the most branches and stuff that I have in this quad tree. So it's like the most complicated one, but yeah, it's I haven't found a real nice way of expressing this thing here. But this is gonna do fine for now. So yeah, let's define this insert quadrant. So it's going to be a function insert to quadrant, and we're going to get the page, and we have the entry and the boundary box. For the entry, we're going to return a bool, and we're basically just going to check each quadrant. Can we insert the thing into here? If we can't, then we try the top left. So can we insert it into the top left? Yes or no? Okay. Yes, then we quit. No, then we test the next one. So the top right. Yes, we can insert it into here, then we quit. Okay. So, and so forth. So what we can do is just say, well, I want to insert into page. So we can reuse this function. And the page is going to be the quadrants. And we have a question mark because it's nullable. So we unwrap that and we pick the top left one, top left page there. And we just pass in the entry and the entry AB that we need. And now what we can do is we can say OR, which basically says that if this didn't succeed, we're gonna try the next here. So we're gonna try the top right quadrant. And if that fails, we're gonna try the bottom left quadrant. And if that fails, we are going to try the bottom right. If that fails, then we return false. Yeah, and that's basically that function. All right. So yeah, let's define this subdivide function as well. Subdivide. So what this is going to do is it's going to create all the quadrants needed for the page and store it in our page list as well. And we already have the boundary box subdivisions, so I'm going to store them in an AABB subdivision variable like this. So this is a subdivision of, well, it doesn't say here, but it is a subdivision of AABBs. Yeah. And now we can simply create the subdivision quadrants, or maybe quadrants is better name. So this is going to be a subdivision of pages. And we're going to create a top left quadrant. It's going to be, so we don't have this function yet, but I'm going to create it later. But we're going to have an add page, which is basically just going to have take in the boundary box. So it's going to be subdivision dot top left. And we'll do the same for top right, bottom left, bottom right. Bottom left, top right. So top left, top right, bottom left, bottom right, yeah. And then we store this quadrants in our page. So now quadrants is not null anymore, it's populated with the children of the page. And then we can return this if we want to have it. I'm not sure if we actually use that anywhere. Let's just not return anything, and we don't have to worry about that. So yeah, so now we can actually do our subdivision. We can insert into our subdivisions. We just need to define a couple of more things. So let's define the add page. So what add page needs to do is we need to get a boundary box. And we're actually gonna return the pointer to the page that we created. And so, right. So what we need to do for creating a new page is we need to extend the both pages array with a new page. We also need to extend the entries array with new entries that's gonna live in the page potentially. So we're gonna have the entries buffer or slice, and it's gonna be entries and items. It's an array list, and now we actually need something to keep track on where our current what our current sort of index into entries are, because we actually want, well, this is basically a little bit for optimization purposes, but I'm just gonna store a current entries index here. Gonna be usize. We also need it same for the pages, and we need to set those to 0 at first. And oops, like this. And then also in the reset, we need to set them to 0. Don't get any weird out of bounds stuff. All right, looks good. Okay, and now we can use this here. So we actually, the slice is going to be this, the slice is going to be put into the page. So this is going to be the slice that the page is going to have be able to use to add entries into it. So it's going to be 10 wide, because that's how many we say is going to fit into a page. And the start of this thing is going to be at the current entries index, which starts at 0 at first. And then we're going to end it at the index plus max entries in page, which is 10. So it's going to be 10 wide with entries. And to be able to do this, we also need entries to be resized. And what resizes does, if it's not set to 0, is it actually appends items into the array, except they are undefined. But we don't care if they're undefined or not, because we keep track of our own index. So we can just use resize because it's faster than to use the append and stuff. So we're gonna do self and resize, and it's gonna be the current entries index plus max entries in page. So that's how many we actually need to have. We need like how many do we have now and how many do we need. So that's that this will ensure that we actually get a slice that's invalid memory, that's in a valid memory location, not invalid memory. Depending on how we say it, can mean different things. Okay. So let's see. Boundary. Okay. And now we have our entry slice, and we can do. We also need to resize pages. So we need to say pages plus one. Because we're adding one page. And then we can say pages.items self current pages index. So this is our newly created page, so to speak, or the space created. And we can say that this is going to be a new page here. And we're going to put the boundary like this. And the entries is going to be a slice array list entry. And we initialize it with the entries slice. All right. We don't have this array list yet, but we're gonna define it. But before that, we're just gonna create this function completely here. So we have the page pointer, which is gonna be the result that we're gonna return. So this is just the address of self pages in the items, and then the pages index, which is the one we defined up here. So that's our pointer, and then we return this pointer. But before we return it, we also want to increase pages index by 1 and the entries by the max entries in page, so that we have the correct indexes updated and everything there. All right, we're almost done. It's not much left. We need to define this slice array list. So I mean, I've basically already done that. I'm just going to show you the I actually called it buffer array list, but I think slice array at first, but I think slice array list is a better name for it, since we're using basically taking in a slice and we're operating on a slice. And what it does is very simple, actually. You can pass in whatever type you want, as an array list can as well. We have a buffer, which is just a slice that you have, and then a length variable, which keeps track on how many items we've added into the slice. So at first, we just assume that you have 0 items in the slice, and the slice is actually just going to be populated with whatever you pass into this function, which is append. So we append an element t into the slice. I also have some asserts in here just for debugging purposes. Asserts are really nice, by the way, to catch things happening when you have a lot of stuff happening at once. So I usually put some asserts in just to make sure that we don't get some weird behavior later on. So, well, in this case, it would be like a buffer or array out of bounds error or something. But anyway, we put well, actually, maybe it won't, because I'm not sure if it checks the individual slice or if it just checks the original array that you're in or something like that. I don't know. But anyway, because we're like, this slice is basically one slice of the whole pie, so to speak. It's one slice of this whole entries array. So the entries array is basically like thousands of objects, but each page is looking at 10 of these objects at the same time. We're looking into this list for each page. And this is the structure that we use to work with it. So we can append stuff into the slice, and we put the element into the buffer here at the index that we're currently in, and then we increase the length by 1. And that makes us also able to check the current length, which is nice. And then we have swap remove, which is just an operation that returns the element of a certain index, and it also removes it from the list, and it also swaps so that there won't be a hole in the list. It swaps in the last item of the list into the list, or into the index where you removed. So, and then it also reduces length by 1. So it's a really fast remove operation, but it changes the order of the items. So if you're not worried about the order of the items, then you can use a swap remove. If you are worried about the order of the items, then you can use an ordered remove, but I haven't defined that yet, but because I don't really need it right now. And then we can also return the items, which is basically the actual items slice, or it's a slice of the buffer where you actually have these items defined. Because if you don't use this and you just use the buffer, then you get probably stuff that you don't want, since you haven't defined it. So you can use items here to get a slice that that points to the actual items that you have put in. So let's import the slice array list. Import, and this lives out here in this file. Need to rename that, but anyway. Right, so now we have our slice array list. We can add pages, which also populates the entries array. We can subdivide, we can put stuff into quadrants. Let's see what we need. We need to flesh out this function as well. So I think that's all that is left, actually, basically. And then there's just then there's a little bit of optimization that I want to do as well. Let's me just see. So yeah, the way that this oh yeah, I forgot also. Of course, we need to define the intersection functionality as well. But anyway, so we have our page quadrants. If we have our page quadrants, we want to insert something into the page. We have our page quadrants. Now we say we try to return into one of the quadrants. So we'll just try that. If we cannot do it, then we return false. Wait, why are we? No. If we did insert something into the quadrants, yeah, then we return true. Yeah. So then we're done, basically, because we're somewhere in these quadrants it's been inserted. If we cannot insert it into a quadrant, that means it can only exist, it can only fit into this page. So first we're gonna check if can we accommodate this. If we cannot accommodate, then there's basically nothing we can do, actually. So we have to return false here. So this means that we're basically going to have an orphan in this case. I should probably log that. Because in this situation, you're going to have a body that's not part of the collision detection. which is bad. I think I'm gonna log this. Say entry did not fit into any page, and we're gonna say yeah, I'm just gonna log it out as a warning. Oops, warning, so that it's visible, and if it happens, then that means you basically need to increase like the maximum entries or do something like that. So hopefully this won't happen. And then we have to return false as well. Say that we cannot insert. Otherwise, we can accommodate because we've checked up there, and then we can just do the same thing as we do down there. So we just append it down in there, and we return true. Okay. So for the insert function, we basically start at the root, go in here, we check if it can contain the AAVB. If it can't, then we return false. Which in the case of the root means that actually let's do this. So if we wasn't able to put it in, yeah, let's actually move this out here. So yeah, so if we, because we always get this result here, so if we couldn't add the item, we actually want to send out a warning here. Okay, and so we send in the page entry BB here, and we check if we can't contain, then we return false. Otherwise, we know that we can contain, so either we contain it in one of the quadrants or itself. If we have quadrants, that means we need to check each quadrant first. So we try to insert it into a quadrant. If we can, then we just return. If we didn't insert it into a quadrant, we get down here, we check, can we fit it into this page? If we can't, then we have to return false. If we can, then we do it. Otherwise, here we don't have any quadrants, but we can accommodate, so we don't have to split. Then we actually just append this entry into this quadrant or page, sorry. Otherwise, we actually get down here, and this is where we need to split in order to fit this entry. So we split here or subdivide into 4 quadrants. We populate them, and we try to also insert the entry into this quadrant here. And then we have these to-dos, which are basically a bunch of edge cases. But I don't think we need to worry about those for now. All right, so back to our populate function. So yes, that's right. We need to start somewhere. We can't just start insert because this assumes that we have a root. We haven't defined this get root function. So before we do this, we actually need to, after we have reset, we need to create the root page. So we need to do an add page, which is going to be the boundary. So this is going to be a root page, and it returns a page. So we have to do this. Right. Now, this should have a root page. This should now get a root page from here, self get root, except we haven't defined that. So let's just define this one. We don't need any parameters. We're going to return a pointer to a page. And this one is just going to return pages items 0. So that's the first page that's defined is the root. We don't have any pages after we've reset. And when we add the page, it's the root page. So yeah, now this is fully functional from a populate standpoint, I think. Let's just go through this. Oh yeah, we need to add this here. And then let's see. Oh yeah, this can throw an error, so we just cache unreachable here because it's the easiest way to deal with this right now. It's just gonna fail if it runs out of memory, which hopefully doesn't happen. Anyway, get root. Yeah. So I'm already actually using this quad tree from outside here, but I have defined it now, and I have defined a populate. The thing that's missing is the intersection part. But what I think is I wanna show how this looks first. So I'm gonna go into our draw function or draw system because this is where it's complaining, and it says that get root is not marked as pub. So yes, I've already implemented a way to draw this quad tree, so I'm just gonna show how it looks. Get root, this needs to be public, and now we do have, yeah, we have this because we haven't implemented this yet, so I'm just gonna say that it doesn't run. Yeah, like this. Okay, so now we can actually start this and see how it looks. And let's run it. And actually have a debugging scene where I add a bunch of bodies. So hopefully it will show up here. Oh, there's an error here. Index out of bounds. Let's see. So we've got quad tree at 116. Okay. It's out of bounds from the draw, yeah. Oh yeah, we're not populating this now like I did before. Okay, so I need to just go in here and fix it. We have our Qt here, and let's just not bother with this, and we'll just do creation container tree populate with boundary and the bodies. All right, this should maybe work. Error unions ignored. Oh yeah, this needs to be cache unreachable. This needs to be cache unreachable. Anything else? Inserted quadrant. Oh yeah, we need to make these like this, and this should be like that. This actually is not public. Okay, now we don't have any errors left, so let's run it and hope that it works. Oh yeah, and here you see it's running a bit slow. Oh. Okay, there might be something wrong with it's not running any collisions right now, but it's and also it's kind of slow, and I think I know why it's slower. than my other test. But what I'm gonna do is I'm just gonna lower the amount of bodies that I'm adding here, just to show how it works. Yeah, so here you can see I have this visualizer for the quadrants. And yeah, well, you can see we also get this warning here, but yeah, so this green is the boundary of the entire, this is the root. And then we've actually added enough bodies to split this into 4 quadrants. So that's the blue squares here, or the the blue lines. And then each blue has been split in these places into these red squares. And then I can also add a bunch of bodies like this, and you can see that it continues to create these quadries like this. All right, so that works. Yeah, and it doesn't check any intersections yet, but that's what we're gonna implement next. So let me go to the quad tree implementation here, and we need to implement that. So let's do it here. So we need a function called intersecting. That's what I called it. And we take our pointer to ourselves because we need to modify a buffer that I'm gonna define as well. I'm gonna go through that as well. So we're gonna send in the rectangle basically that you want to check for. So which bodies intersect with that rectangle? And we're going to return a list of intersections, which is going to store a type or a value here, which is basically the pointer to the entry type thing, which is a body. We don't have intersection. Well, we do have intersection actually. I can import it like this. What it is basically just a struct that holds the entry. It holds the collision information, which is, we're not going to go into that right now. But so for the intersecting part, well, most of this is actually implemented also in the AABB structure. So I'm not going to go through like collision detection and that. I'm just going to say that are these rectangle intersecting, then we put them into this list, because that's basically what the quad tree is there for. It says that, okay, these rectangles are colliding, and then you need a more sophisticated like collision detection system that actually checks, because you can have like circles, you can have different types of shapes if you want to have collision detection for like more complex like polygons or whatever it's called. Yeah. But this is just going to check for rectangles, and so this is basically like a broad face, you can call it the broad face, where you eliminate all the bodies that you don't need to check basically. And so yeah, this is basically what the quad tree is good for. So yeah, first of all, we need the buffer to store the results in. So let's define the intersecting buffer, which is going to be, this is going to be an array list of intersection star t. And we need to define it here or initialize it here. So let's initialize that. It's going to be intersection. Let's just have some sort of capacity as well. And it's going to be let's just do, I don't know, 100. And yeah, that's gonna be fine. A reset, we also need to resize this to 0, catch unreachable. Deinitialize, we need to deinitialize. There. All right, so let's get back here. And first thing that we're gonna do is we're going to we're going to reset this buffer. So we resize it to 0 so that we can put the intersecting results in there. And so I've made this guard here basically that says if we have no pages, basically is what this means, then we just return an empty list. And you can do that in SIG like that. So it's an empty list with no items in it, and that's fine. And but if we do have pages, then we need to basically do the same pattern as we do with insert. We need to start at root. We need to check intersecting for each root. So I called it intersecting for page. We pass in the target rectangle, and we pass in the root object. And now after we've done that, we actually have all the intersections that we need. And so we can return the buffer items to the caller. And now we need to also implement this intersecting for page function. So this is going to be QT there. We're going to take in the target rectangle. We're going to take in the page that we're looking at, and void, because we are populating the intersection buffer. So we're not going to return anything. And what we're doing here is we're checking first if we don't intersect with the target. So if the page AABB, if the page boundary does not intersect with the target, then we can skip this entire page. Then we just return. So yeah, that's what makes this powerful, because we can eliminate a lot of checks by doing that. Otherwise, since each page has its own list of entries, we need to check page entries items. And yeah, and this is the this comes from the slice array list, so that's why it looks like this. Here we actually get the entries in the page, and here we check if we get intersection. So this is a different function from up here. This returns a bool, and this returns an actual intersection. So it does a little bit more of calculation to actually get the intersection. So we can say we get an intersection here. This returns a nullable. So we get the intersection out like this. We capture it here. And then we can just append this into our intersecting buffer. So we append, and we need to create a new intersection. Entry is going to be entry.value. This is our pointer to the body, basically. And then we need an axis. So now we basically just copying the values from the intersection that we got from the AABB structure, like this. All right, so now we have our intersection for the for this entry. And yeah, we also need to catch unreachable here because we're calling append. All right. Now, we also want to say, we checked all the entries in the page, but there can be more entries because we have quadrants, possibly. So if we have any quadrants, we've not checked them. If we have quadrants, then we say, we can just call this again, intersecting for page recursively. And we're checking for this target, and we need to pass in the quadrants top left, which is a page pointer. And that's for the top left, and then we need to do top right, bottom left, and bottom right as well. So top left, top right, bottom left, bottom right. Okay, and then we're basically done with the intersecting part. So we're checking for intersections for this target rectangle. We are going into this root to start with. And if we don't intersect with the page, we just return. If we intersect with any of the children in this page, we add them to the intersection list. If we have quadrants, we're gonna check the same thing for all the quadrants as well. Right? So what this really does is eliminates a lot of checks if you're gonna compare it to a brute force algorithm. And now I can actually use this as well. I think I have, let me go back because I had this older code here which actually use this type of check as well. So I'm populating the tree. I am going through each body, and yeah, don't worry about this code. I'm not gonna go in depth here, but we're basically populating the tree, the quad tree, with all the bodies. We're going through each body here, and we are checking collision for each body. And what this does is it actually calls intersecting from the tree in the end. And so it actually uses the intersecting function. So let's fix up these errors. Right, action ratio. And that was it, it looks like. So let's see if we get any collisions now. And yeah, looks like we got collisions here. Cool. So yeah, and you can see as things disappear from the quad tree as well, it updates, or well, it rebuilds into a different quad tree. So it removes, or yeah, it looks like it removes the quadrants. But yeah, there's the implementation of the quad tree, and there's some optimizations that you can do. I've got it up to working with like 500 bodies without going into the, or 1,000 bodies without going into some really low FPS. It keeps at 60 FPS, although it's not actually as performant as I would like it to be yet. I think maybe I haven't done any profiling on it. Maybe you can improve like the times of building the tree or querying the tree with some sweeping, but yeah, at least it works, and it's actually a lot better than my R3 implementation, which I realize now that maybe I should actually, for the R3, you can actually do something else. But yeah, anyway, yeah, that's gonna be it for now, and maybe we'll go through some optimization techniques that you can do to improve this even further. Just some quick optimizations to make it a lot better. Yeah, that's it for now. And have a nice day and see you next time. Bye.